The last thing I want to talk about is what's known as Chateliers Principle. And Chateliers Principle says if a system's at equilibrium and it's disrupted by something, either by a change in temperature, the addition of a reactant, whether it's a gas or a solution, that the system will move to reestablish equilibrium once that disruption has been introduced. So if you've got a reaction at equilibrium, you do something to it, forces it out of equilibrium, what happens is nature's going to reestablish equilibrium. It's going to find that new balance. And so we can stress chemical equilibrium in a number of ways. And there are three ways. So changing concentrations or pressures, causing volume changes in gas phase reactions, and introducing temperature changes. These are three ways which we will stress chemical reactions to cause or force a reaction to move in one direction or another. So, for the reaction involving nitrogen monoxide and O2 to produce nitrogen dioxide, we could increase the pressure of nitrogen monoxide, for example, and force the reaction to go to products. Just like adding oxygen would force the reaction to move towards products. On the other hand, we could increase the NO2 pressure for some reason, and that would force the reaction to make more reactants. So increasing something pushes the equilibrium away from the side that is being added to, and likewise what happens is you can, if you remove something like oxygen, so you take oxygen out of this reaction, then the reaction moves to reestablish it by compensating for the loss of the oxygen. So adding, you've moved the reaction to the other side. Taking away, you bring the reaction back towards it. Volume changes affect gas reactions. They don't affect reactions in solution. But basically, when you have a volume change with a gas, reducing the size of the canister that the gases are in will cause the reaction to move towards the side with the fewest number of molecules in the balanced equation. On the other hand, if you increase the volume, then the reaction moves towards the side with the greatest number of molecules in the balanced equation. So again, if we go back to our nitrogen monoxide oxygen reaction, what would happen if we increase the volume of the canister in which this reaction occurs? Well, more volume means more molecules. And so increasing the volume, moves the reaction towards the reactants, because you have three reactants versus two products. On the other hand, if you decrease the volume, the reaction moves towards the product, so you have fewer collisions. Finally, we have temperature change, which is really just heat flow into and out of a reaction. And so we're talking about enthalpy change, so you need to know delta H of a reaction. And if you recall what you know about enthalpy, that positive enthalpy values are endothermic reaction, meaning that heat is a reactant. So if you see a positive delta H, just go ahead and write plus heat on the reactant side. It makes it a lot easier to see how temperature changes will affect it. On the other hand, if it's exothermic, delta H is negative, and so heat is a product. And so this is how you can track the effect of increasing or decreasing the temperature on a reaction and what it does to the equilibrium. Now, originally we had talked about Haber's process and how he scaled it up, the ammonia production up from 125 milliliters per day to something like 20 tons per day. And what was used is a device that looks something like this, and this is still used widely today for the production of ammonia, which is one of the top 10 molecules produced worldwide. And again, agriculture is one of the major reasons we use it. And so what happens is we have an inlet of nitrogen gas from the atmosphere and some hydrogen. We inject it into this temperature chamber here, and this temperature chamber is around 500 degrees Celsius. So what we saw earlier in the chapter is at this temperature, the reaction is very reactant favored, but we do make a little bit of product. And so this gas gets blown in through the column. It passes through a catalyst chambers to help facilitate the ammonia production, and then it's blown out into a secondary chamber here, and it cools. And in this chamber, it cools to the point where the ammonia condenses into liquid and is removed from the gas phase. So our reaction is out of equilibrium, and so the gas gets blown back into the hot chamber, and this just constantly cycles and cycles around, producing ammonia on a large quantity.